distribution. And I'll post the key. You guys can look at what I wrote up for this. Yeah, so assuming you have sampling distribution of the mean, I'm just gonna.
Which is different than a Z distribution, right?
Yes, and no. Yes, because the units are different, so it's centered at mu.
Whereas a Z distribution would be centered in 0.
Yeah, and it has a standard error or standard deviation. So this is a sampling distribution. So the standard deviation equals the standard error, which equals sigma over square root n. So this has a non-1 standard deviation and a non-zero mean. So it's just a normal distribution. That said, when we're dealing with sampling distributions, we usually want to work with the standard normal distribution. So we divide by the standard error and subtract the mean. So like when you calculate a Z statistic, you're doing that transformation. You're going from the sampling distribution of the mean to the standard normal version of the sampling distribution of the mean.
Yes, okay.
All right, but for now, we want to basically, for this example, 6 and 7, we want to be working with this distribution in terms of the mean and the standard error, and not in terms of the standardized units. So what we're doing in those examples, I believe what I had you do was, okay, well, you want to find the values of sample means. So you want to find x bar, I'll call this x bar 5, that has some value that cuts off the lower. Wait, did I use 5 or no? 2.5.
Yeah, 2.5.
2.5.
All right,
This is 5%
that's
total.
confusing. So I'm just going to call this x bar L for low. All right, so this has 2.5% in this lower tail, and x bar high H that has 2.5% again in the upper tail.
Yep.
Okay, and yes, so let's go from there. So the first thing we needed to do was figure out what XL and XH were.
Yeah.
So we have to go through 6 to go through 7. So we're gonna just start from here.
Okay.
All right, so what we do is we start off, well, we need to know what Z values correspond to the low value, so I'll call it ZL and ZH. And these should have 2.5% in the tail. How do we get these values?
1.96 and negative 1.96, right?
We look at the Z table.
Yeah, we look at the Z table
Once
and then
we
we
get to Z
see that this is negative 1.96 and this is plus 1.96. All right, great. So we have a Z value. We know that Z equals X bar minus mu over, what goes on the bottom?
Standard error, so sigma divided by square root of n.
Well, over square root of n, and that's because we're dealing with
Sampling distribution.
Sampling, I should write it all out so no one's confused. Sampling distribution of the mean. Okay, great. So we know everything here. We know Z, we know mu, we know sigma, we know n. We just need to solve for X bar. All right. So we do that for 2 cases. Actually, I should write out what we have here. We have sigma's what, 10?
Sigma was 10, yes.
Yeah, and mu is 100. And what was our sample size?
16.
At least one of the numbers is easy to deal with. All right, here we go. Actually, those are nice numbers. Alright, so let's start with Z low. We know that that has to be negative 1.96. Actually, I'll write this out symbolically first. Okay, so we want to solve for x bar. So the way we do that is we multiply over, so we have z times the standard error. And yeah, then we add
Plus
the mean here. So z equals the mean plus this, right? So z is actually the same for the low and the high, right? So it's actually just plus or minus
Right, 1.96.
z. And this is almost the formula for a confidence interval. We'll go over a confidence interval. The difference is a confidence interval, you're calculating to estimate the mean. So you don't know the population mean, you use a sample mean. So that's the difference. And basically what that does is it gives you kind of error bars around what you think the mean might be. But it has this kind of complicated interpretation. Usually we just say, we get the confidence interval, which is just two numbers, and you say you're 95% confident that the true population mean lies in that interval. What do we mean by 95% confident? Well, it's complicated. What we actually mean by 95% confident is that 95% of the possible samples will have a mean that would produce a confidence interval that contains the true population mean. And the reason we have this kind of complicated interpretation is that we can't talk about the probability of a population value in frequentist statistics. Population value is some number. It doesn't vary. It's not a variable. So it's not something that has probabilities. It just is that number. The problem is we just don't know what that number is. Does that kind of make sense? We'll talk about it next week. This is not going to be on your exam. All right, good so far?
Mm-hmm.
So if we want z low and z high, did you guys already do the math? Because I don't really want to do it. What is z low?
95.1
Mm-hmm.
and 104.9.
0.1 and z high. Sorry, what was this one?
104.9.
They're like 0.1 above and below the two standard deviations, I think.
0.1?
9.
0.9. Yeah, okay, that makes sense. Alright, good. So we've got those two values. So what do those mean? Well, this means that we'd have 95% of the possible sample means of size 16 between 95.1 and 104.9. Okay, that's helpful, right? If you know the population mean, you can figure out where 95% of your possible sample means would be. What we actually want to do with confidence intervals is kind of figure out the question in reverse. So if you have a sample mean, where is the population mean? And like I said, it's complicated because we can't talk about the population as being a random variable. We can only talk about the sample mean and these values that we calculate using sample values as varying randomly. So we can talk about an interval varying randomly, but we can't talk about the population mean varying randomly. Unless you use Bayesian statistics, which relies on conditional probabilities. And I'm throwing in that caveat like all the time because everything we do in psychology is frequentist, and it's starting to like become apparent that there's in some ways a nicer way to do it in Bayesian statistics. In other ways, there's problems with the Bayesian statistics. But keep in mind, there's another way to do this that we're not dealing with right now. Good?
Good.
All right. So the next question I think is, well, what happens if we center this interval at x bar instead of mu? right? Can somebody give me the assignment? I wanna see what the questions actually.
Yeah, read it out loud
Because
for the video.
there's definitely some
Don't
complex.
read the answers, just.
That's fine. Alright, so suppose we didn't know the population mean and we calculated this interval using a sample mean. Would the width of the interval be different? Yes.
No. It'd be the same because the sample size is the same, right? According to the
Right.
inverse.
So sigma doesn't change.
That's what I said.
That's what we said, yeah.
And I think
We were being argued the other way.
because the sample size is the same size, right?
Yeah. So the sample size doesn't change. Does the critical value change? So we're still
No, because we have the
asking
interval,
what is
right?
the critical value based on? So I'm asking basically, okay, we have this formula, this is really important, put a big star next to it. What if instead of this formula we look at this one, z equals x bar plus or minus z times sigma over square root n. Okay, sorry, that's getting hard to see over here. Yes. I'm not sure if it's any skinnier or deep as it is wide. Ancient TV. Alright, well that gave us a few inches. Alright, so what determines the width of the interval?
Sample size.
This
The
term,
Z. Oh, sorry.
this whole term, right? Because it's plus or minus this.
Yeah.
So we have a midpoint, and then you're adding the same one thing, and you're subtracting the same thing. So the width is entirely determined by z times sigma over square root n, right?
Mm-hmm.
So the only thing we're changing is the mean. So we're only moving the center. The width of this interval isn't changing. We're just shifting it left or right. Did everybody see that? You guys saw it. Does that make sense? Yes. Yeah. Okay.
Well, I knew it, but I didn't know why I knew it.
Yeah, it helps to have the symbolic notation sometimes, and I think this case is one of those where it's tricky if you don't like think about this margin of error here, which is hard to do if you haven't studied confidence intervals before, which is why this is kind of above and beyond what you would normally do even in statistics classes. They don't usually teach where this comes from. I just think it's complicated and kind of interesting. So anyway, so let's look at it. So suppose that we were to repeatedly draw samples of size 16 from the distribution described above. We know that 2.5% of the sample means have values less than the percentile calculated in 60 whatever, and 2.5 have percentile values calculated greater than whatever. That makes sense, right? We're just saying that 2.5% are down there, 2.5 are down there, and I was trying to word that in a way that didn't actually give you the answer as to what these two means were, or two.
Right.
Oh, I wrote Z here. These are mu's. I hope that wasn't confusing people. Right? No, these are X bars. X bar. Wow, that really doesn't erase very well, huh? But yeah, so this is the lower sample mean, this is the higher sample mean. Alright, good?
Mm-hmm.
That wasn't confusing people, was it? I hope not. Okay. Alright, so the width of the interval doesn't change. That is 5% of the sample means will reside outside of the interval. Given your response about the width, which we said doesn't change, if we were to use any of the means in this 5%, so the means that land out here or out here as the center of the interval, would that interval contain the true population mean mu? No, right?
No, because it's way over there.
Yeah, so the width of the interval.
It's the whole deal about a confidence interval, right? You're being able to say that within that 95, you're 95% certain that within that range, you're able to properly say that that's where the true population mean is. So if you're pulling from the two
Right.
outlier ranges, then obviously it's not gonna be in from there, right?
Thank you, Professor.
Yep, see ya, good luck studying. Alright,
No, repeat that, why again? I missed that, I don't understand.
okay, yeah, sure, so let's look at y. So the width of this interval, is this distance, right?
Mhm.
And this is half of the distance, right?
Right.
So you can imagine that if we move the center to somewhere over here, the bound on this side would be, so if we looked at like a mean that was here,
Mhm.
the width of that interval would be this, so it would come out to here, and this, so it would come out to there. So since this distance here is the same, right, the width isn't changing, the interval would be like that. It
Right.
wouldn't contain the population mean.
Okay.
Right, so that's kind of the conceptual interpretation. You can look at the numbers and they work out too. But because, this is the same whether it's here or here, this interval centered out here would not contain the true population mean. Do you see?
Yes.
Okay.
So what that effectively means is that the 2.5% over here and the 2.5% over here, those sample means would, if you had samples with those means, those samples would not result in confidence intervals that contain the true population mean. So what we're saying is if we use this method, plugging in a sample mean, 5% of those possible samples we could have will result in intervals that don't contain the true population mean, whereas the other 95% will contain the true population mean. Does that make sense?
Mm-hmm.
So that's a confidence interval. That's where the logic comes from, and that's why we have this really complicated interpretation. 95% confident. Make sense?
Yeah, so the answer to 6 would be no then.
6. 6 is a
Uh,
series of questions.